So today we're going to learn about the yield of a reaction. There you can see it right there. And we're going to be talking about product. So we're going to be talking about the products, the right side of the chemical equation. And we're going to be wondering whether a chemical reaction that we actually do in the laboratory was done well, all right? So we know how to do stoichiometry. Stoichiometry is a calculation that involves a balanced chemical equation, that involves our calculations with moles and grams and the mole ratio, and it allows us to predict how much product that we're going to make in a chemical reaction, right? Really, if we talk historically, and I've talked to you a little bit about how Lavoisier was really super important, and whenever I say Lavoisier's name, I like to show you his picture just because that's fun, because I spent a lot of money on these books in university, and I'm going to get mileage out of them. That's why I hold up this book every time I say his name. Lavoisier did for chemistry what Sir Isaac Newton did for physics. He turned chemistry into a true science in that through his calculations, he could predict how much product he would get in an experiment. And if you can predict things using science, then that's very important. It means that you can build machines that will behave the way you want them to behave. You can do chemical reactions that will produce products that you want, that maybe you can then sell to someone, and then you've got an awesome business like Dow Chemical and all those things. So what we can do at this point using stoichiometry, if we have a chemical reaction and we know how many grams we're starting with, we can, through our calculations and our maps, figure out how many grams of product we predict to get if we've done the experiment properly. What we're talking about today is, what if we did the experiment? What if we actually did that experiment and got a certain mass when we were done? We weighed it on a scale. What we want to talk about is, how well did we do the reaction? How well was our yield of that chemical reaction compared to what we predict when we do stoichiometry? So we want to look carefully at what we get as the product, its yield. Now let's go through some definitions here. We'll define what yield is, and we'll define what a theoretical yield is. Yield is the amount of product that is obtained in a chemical reaction. Typically expressed in grams, because we can weigh that. The theoretical yield is the amount of product that we predict we should get based on stoichiometric calculations. Again, stoichiometric just means our calculations with balanced chemical equations. Using the balanced chemical equation, sometimes it's called the calculated value. And we know how to do that. We're going to do a couple of examples today where we're going to do that calculation that we learned the other day that then you completed the assignment in order to determine the masses. It's going to involve our little moles, grams per mole triangle, the molar mass triangle, and the mole ratio. So we know how to calculate the theoretical yield. That's what we've been doing. Why is it called theoretical? Because all of this calculations that we do are based on our knowledge of the periodic table. We get the formulas from the crossovers, which come from the fact that they have electrons and they gain and lose them. And we believe they have electrons in certain orbits because that's the theory Bohr told us. So all of these calculations, all of those masses, all of those charges come from an idea that Bohr expressed to us. And so when we use these calculations, we get the theoretical yield. It's what our theory predicts. Okay? When we actually do a chemical reaction, we get the actual yield. Sometimes it's called the experimental yield because it's something that comes from an experiment. In tomorrow's experiment, we're going to start with some sodium bicarbonate. I actually have some here for a different demonstration. We're going to have it undergo a decomposition reaction, and then we're going to weigh the product. We're actually going to put it on a scale. We're going to get a number in grams, and it's going to be our actual yield. In tomorrow's experiment, I'm going to give you two possible reactions. You'll find two theoretical yields, and you're going to try to determine which reaction took place. So the actual yield is actually obtained from experiment. These words right here you will see in our questions: actually, obtained, experiment, measured. Those words will give you a clue that we're looking at the actual yield. So we're going to have a theoretical yield, what you would get if you did it perfectly. We're going to have an actual yield, how we actually did. This is very much like a test. We've already talked about percent composition. If we have a theoretical yield, something that we would get if we did it perfectly, and an actual value, we can express our yield as a percentage, kind of like a little grade on how we did on the experiment itself. That particular value is called the percent yield. And it's just like any percentage that we've done. If you actually get 8, and the assignment was out of 10, then you have 8 over 10, the actual amount you got correct, over the theoretical amount that you could have got if you did it perfectly, times 100, 80%. Yeah, pretty good. We will do the same with percent yield. We will have an actual that we get from an experiment. We will have a theoretical, which we get from our calculation. And we have then a percentage yield. And it expresses how efficient our chemical reaction is. Not the reaction itself, but the procedure and the reaction kind of all put together. In university, whenever we had to calculate percent yield, mine was terrible. I was not good at being an experimental chemist. I was not patient enough. I never measured carefully enough. I soon got out of the experimental business and got into the theoretical chemistry, where I then just had to use equations and calculations and right or wrong, and now I'm a teacher. No, to be a good experimental chemist, you need to be really patient. You need to be really good with your hands, that you know where everything goes. You can't be spilling things. You can't be, it's like what makes a good chef too as well, right? They've got to know the exact amounts to put in there to make it good. Before I actually show you a little demonstration and do the calculations, actually, I'm going to show you the demonstration in conjunction with this. I want to talk about why your yield might be low. All right? Well, sloppy work in the laboratory would be one reason, and I'm going to talk a little bit about this. That's what my next slide is. And then we will use this equation. So what I'm going to talk about in the next slide is really kind of giving you some ideas for an error analysis. If your percentage yield is off, then you're going to want to ask yourself as a scientist, what went wrong? Where could we have lost some of this mass? Why don't we have a good percent yield? And really, that's what an error analysis is. What went wrong? Let's think about what went wrong. What was the reason? How did it affect my percent yield? What could we do to fix it, make it a better experiment in the end? So let's talk about some of those things. And again, I have no idea where anybody is. Is anybody still writing this slide? We've all moved on to bigger and better things. So let's write this all down, and then I'll show you a little demonstration on how these things can manifest themselves. I'll show you some of the equipment that we're not going to use this tomorrow because we're going to do a different one, but I'll show you why and how. Many labs can suffer from these problems that I'm going to demonstrate here. So what can affect a percent yield? Why might a percentage be low? Well, in this quick little demonstration that I have here, I can illustrate most of these failures quite easily. So what I have here, and I'll put some goggles on because I'm going to start working with some chemicals, but they're pretty tame. So what I have here are two chemicals here, and I'm going to put them together to perform a single displacement reaction. And I have some calcium chloride, which I've dissolved in some water, and then I have some sodium bicarbonate, which is baking soda, which again I've dissolved in some water. And here's the sodium bicarbonate. You can see there it's very fine. And here's what the calcium chloride looks like. You can see there it's made up of almost little pellets of the calcium chloride. Now, to be honest, when I use sodium bicarbonate, which is baking soda, and we're going to use that in tomorrow's lab, we're not going to do this experiment, but we're going to do a different one using sodium bicarbonate. I go and get my sodium bicarbonate when I need more for the science department from the grocery store. I go to the grocery store, I get a box that says baking soda, I buy it for $1.50, and I have 500 grams of baking soda for $1.50. If I want to order that through a chemical supply company, that 500 grams would likely cost probably $10 for 500 grams, because they are going to put it through they're going to do some tests on it and put a label on it and make it look really nice and really neat. So what's going to be the difference between this sodium bicarbonate and the other sodium bicarbonate? Well, this sodium bicarbonate probably was made using a procedure that doesn't necessarily contain impurities that would hurt us, because this is food grade, but it might have, instead of all sodium bicarbonate, there might be some sodium chloride, maybe some salt in it. There might be maybe a little bit of potassium chloride. Again, these things are not harmful to us, but they might contain some impurities that aren't sodium carbonate. So when I go to weigh some of this sodium carbonate, maybe as my reactant, and I weigh it on the scale, what I think is going to be 5 grams of sodium bicarbonate might be a little less than 5 grams, because I'm weighing some other stuff. It's not pure. If I were doing experiments at a university level, or perhaps I was going for my PhD and I wanted to discover something new, then I might want to spend the money on the most pure reactants that I can afford, so that I can confidently say that my percentage is very good, right? So I would use more expensive reactants. So sometimes reactants aren't pure. Products lost during transfer to another. When we make solutions to do an experiment like this, where we're going to maybe do a double displacement and get a precipitate, we will start with a certain mass of that substance. So here you can see I made a little paper boat. That's the term we use when we make a little thing to hold on to our substance on the scale. If I were to use a paper towel, let's say I were to put some of my sodium bicarbonate on the paper towel, and I were to measure it, and then I were to transfer that into, say, my beaker that I want to dissolve it in. As I transfer it over, everything looks pretty good, but you'll see that something like a paper towel will hang on to the sodium bicarbonate. So if I use something like a paper towel, that's really going to be terrible, because I'm not going to get it all into the beaker. I weighed it here, but it didn't all make it into here. You might think use a piece of white paper, but even white paper is rough enough that some of it will still stick to it. You can actually purchase special weigh papers, and these weigh papers, I don't know, can you see that this side is shiny and this side is not so shiny? So we like to use the shiny side. Again, we can make a little boat out of it. This is one I made a boat out of earlier on. Put it on the scale, tear it, and weigh it, and we can get that. And because it's shiny, the powder will slide off easier. Will it all come off? Maybe a little particle might stick, but it'll be better than what we had with the paper towel. So even in the weighing and the transfer, you can lose some. Let's just put this aside here. So now I've got the chloride here and the sodium bicarbonate there. If I pour a little bit of the calcium chloride into here, actually let's pour it all into here. Okay. Now notice, I've got to wait for the drips to end dripping. So if this was what my reactant was, now there's still some of it stuck in the glass, not in the glass, but on the surface. So I can't get it all off. That means I'm going to lose some of my calcium chloride before I even start my chemical reaction. More stuff lost during the transfer. Did I drip some? So I've lost it on the table. I can't get it back. I could have rinsed this out maybe. Let's put some sodium bicarbonate in there. There you can see we're getting a precipitate forming. It's not as much as I had hoped. I'm a little disappointed in that because I must have diluted it. But there you can see there's a little reaction as well. And we're going to want to get that product. So we've got a precipitate formed, and now we're going to try to get that precipitate. Now, I don't know if you notice it. It was more prevalent this morning, but right away when I transferred it, some bubbles started to form, lots of bubbles. Now, what does that mean? That means perhaps a side reaction occurred. Maybe some of the carbonate that was going to turn into calcium carbonate, which is the precipitate, maybe some of the carbonate turned into carbon dioxide and left. So that means a different chemical reaction than I was hoping for has taken place. And now I've got less of the solid because a side reaction, had some of that substance take away as carbon dioxide gas. So side reactions that you don't anticipate can sometimes change a reaction. So how do we get the solid out of a mixture like this? Well, what we do is we filter it. We use a filter paper, all right? And we use a funnel and Erlenmeyer setup like this. And what we do with the filter paper, you can fold it in half. And another way that you can deal with the filter paper is what we can do is we can flute the filter paper. It's called fluting it. And essentially, you're making a fan, starting from that center point, you're making a fan out of the filter paper. So I'm just flipping back and forth, turning it into a fan shape. And again, some of my chemist friends were much better than this than me, and I'm sucking again as per normal. That's okay. That's why I do calculations. All right, so you make kind of a fan out of the filter paper, and then you can open that back up, and now it looks a little more like a coffee filter. And this is before there were Keurigs, right? I don't know if you've ever seen the old coffee filters they put in the coffee makers. So you've got that nice fluted filter paper, and you can now start pouring in the product, and we can hopefully filter out some of that product, and you can see the filtrate coming through, all right? So again, products lost due to filtration. If you don't have a filter paper that's got fine enough little holes, some of those little particles might get through. Then you didn't catch them, so you need a better grade of filter paper. If you're impatient like myself, you know, if you poured it in too fast and poured it over the edge, it goes around the filter paper, and now that's an epic fail. You see there how it's all white there at the bottom? I completely screwed that up. That is piles lost. What should I do to fix that? I probably should refilter the filtrate, but I'm not going to do that. I just wanted to illustrate to you how you could lose it during filtering, okay? I've even seen students in the past go, why is it so slow? And then just poke a hole through the bottom of the filter paper and like, whoa, now this is great. Works great. I'll be done in 2 seconds. And of course, they've got all their powder at the bottom, and it's no good. So if you don't filter carefully, you can lose some due to filtration. In the end, the way we measure this, I would have measured the filter paper's mass first, then collected the powder, and then let it dry overnight or for a couple of days, and then weighed it again with the solid that was on it. If you're not patient enough and you don't let it dry completely, sometimes it's too heavy, and you've got a percent yield greater than 100 because you haven't allowed all the water to evaporate from it, and so it gets heavier, right? So that's not really a proper percent yield, because you can never have a percent yield greater than 100 because you can't produce more mass than you started with. That's the breaking of the law of conservation of matter. So if you do get it greater than 100, there's usually something else that's been added to it that you didn't think was going to be there. Okay. Product loss due to splattering during the heating process. Now, just for the argument, let's say I did a beautiful job filtering, and this filtrate is nice and perfectly clear. So let's assume that that's true. All right, maybe not quite perfectly clear, but let's assume it is. There would be the other product dissolved in here. There'd actually be some sodium chloride in here. So if I wanted to get the sodium chloride out of this, I would use an evaporating dish. I would put that filtrate in the evaporating dish, and then I would put the evaporating dish on the ring clamp, which I'm not going to do because it's occupied right now. I would put a Bunsen burner underneath here, and we would boil the water away, all right? Now, just like when you cook something, example, bacon, when you get close to the end of the bacon being done, what does that evil bacon do? Right before you're just done the bacon and you're sitting there cooking away and you think it's nice, and then all of a sudden, bang, it gets you. It splatters on you, and then you're mad. You're mad at the bacon, but it's so delicious. You don't stay mad for so long because then the bacon's good. Anyway, all right. It splatters on you. Now, the reason it splatters is because there's a little bit of water left. When you cook the bacon, lots of water comes out right away. I don't know if you've noticed that. It bubbles away with all the water. Then the water starts to evaporate and the grease starts coming out. but the water sits below the grease. It sits underneath it. And that last little bit of water that's hiding close to the surface of the pan gets really hot, it boils, and it makes a bubble and it jumps out at you. When you're doing something like this, instead of a liquid being formed, and you can have a liquid formed like grease, and that'll spit at you, but a solid will be formed. The solid sodium chloride will be formed. There'll be some water underneath it. There'll be a crust, and it will also pop. It'll spit at you, and some of that product will jump out. So some of that product will escape, just like the grease escapes. And if we're trying to measure that, then we're losing product. Then we're losing the product, and the percent yield goes down and down and down. So those are some reasons how you can lose some of the product that you're trying to get. Too many transfers loses reactant. Even when you get finished, let's say I'm still doing this one, terrible, don't mind the terrible work. Look at there, inside the container, lots of product left. We use a glass rod with a little bit of hose on it to work as a little spatula, right? But no matter how hard you work at it to get that last bit out, you're going to then have some on the little spatula and then some more in here. We could rinse and rinse and rinse, but like sodium carbonate is such a fine powder, no matter how many times I rinse, I'm just going to pour it down the drain, that sticks to the bottom. I can swirl it around, I can do all that stuff, and that sodium carbonate is so fine that I need a paper towel to wipe it out. So I've missed some of the product. I can't get it out. So I won't be able to measure it. The percent yield will be off. So percent yield can be off due to many reasons: transfers, filtration, splattering, etc., etc. Okay, let's do some practice problems. I've got 3 practice problems, and then I'll just let you work. Again, there's a sheet on Google Classroom as per normal. And this is the one that I added, that I actually took from my 3U this morning. And this is actually the easiest of the easy version of these types of calculations. The calculation that we're doing is really an add-on. The percentage that we do is an add-on to the questions that we already know how to do. So in this question, I'm just showing you how to do the add-on question, the tail end question. I'm telling you that 2.52 grams of precipitate was actually obtained. Oh, I better do this on the smartboard. I was going to use chalk. And the theoretical yield was 3.01 grams. In this calculation, we don't have to do stoichiometry. I've already told you what the theoretical yield is, and we know that this much was actually obtained. So what we're doing here is just the percentage. It's like we're doing the how well did we do on the test. Percent yield what did I get on the test? How could have I done if I did it theoretically perfectly? Actually over theoretical. Actual yield over theoretical yield times 100 to make it into a percentage. Which one is my actual yield? What number goes on the top? Yep, Jess? Yeah, 2.52. 2.52 grams over 3.01 grams times 100, and we get a percentage. And I don't know if anybody needs calculators. Anybody in a calculator situation? You got a number? Did you say 84? 84? 84.0? So we should keep 84.0%. Again, 3 digits and 3 digits. Again, I'm only going to, rounded to, what is 3 digits? 83.7%. All right. Again, I want you guys to try to get the proper number of significant digits. All right, Jenna and Mark, I'm going to actually mark yours because they should know better as veterans. Okay, so 83%, we don't know enough about this experiment to know why or where they would have lost some of their yield, but we can calculate it. Okay. You know what you can do here? Write down number 2. Write down this paragraph first, then put the balanced chemical equation underneath it, because then you don't have to write it twice. So just write it was found that when 3.31 grams of blah, 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 and then we will write the equation underneath, then we can do the problem there. Saves you writing it twice. And as you're writing, I'm actually going to rewrite the equation underneath because I need to make the math. Just as we have been doing, because in the end, well, you're going to have, you'll know that it's a percent yield problem because it says calculate the percent yield. But to start the problem, we're going to be doing the same calculations we've done. So what you need to get into the habit of doing is, when you get these that have a chemical reaction, write the numbers down underneath them in the appropriate line. Whatever you're given, and then you'll think it through after that. It was found that when 3.31 grams of lead-2 nitrate, 3.31 grams. I write down that mass in that position. When it was heated, the actual yield of PbO was found to be 1.75 grams. Again, under PbO, I would write 1.75 grams. And because we know that it is the actual yield, I will put here equals AY. All right? Now, in order to calculate a percentage yield, I need to find how much of this that would be predicted through calculation, which means when they give you the actual yield, underneath it, I'm going to put question mark grams equals theoretical yield, T yield. Now that's the thing I'm going to look for using our calculations we did the other day. Once I have those two numbers, I'll do my percentage. So now I'm going to build my map just like I've been doing. I can't go straight across, but I can go down. And if I go down, what's it going to become? What's down on that next line? Moles. And what equation do I use to go from grams to moles? I need our molar mass equation. Do you remember it? Do you remember the equation? It comes from the units. I always say, think of the units. Molar mass is equal to grams over moles. Which means if I build the triangle, what's on the top? grams, molar mass, moles. And mine are scribbled in there. I'll put it on the board, make it bigger. Grams, moles, molar mass. That means I'm going to need a molar mass of PbNO3 brackets 2. Then I'm going to go across this way to X moles. How do I go across? What's that conversion factor called? Mole ratio. And it comes from the numbers, right? X over whatever, whatever, whatever. Now I still have to go up. And again, I'm now going to need my equation rearranged, which means I'm going to need a molar mass again. I'm going to need a molar mass of this guy and a molar mass of this guy. That's supposed to be MM. So let's go ahead and get those molar masses so we can do our calculations. Now, it's going to be tight for room. You know what? I'm going to let you guys just do the molar mass calculations, and I'm going to just use that equation up there to write it down. You guys do it off to the side. Same with the lead. You guys know how to do this. O's and P's. Write it off to the side. You've got more room here. I'm kind of stuck for room. And then tell me what you get for the molar mass of lead 2 nitrate and what you get for the molar mass of lead oxide. Because again, like I said, I don't have enough room over there to do that. Anybody have some numbers? No, yet no? Oh, you guys are trying to squint and look at the masses? That's fun. Which one do you want? Lead? Lead is a heavy one. 207.2. 207.2. Conrad, you got any of those numbers yet? Molar masses? None? I thought you'd be done all the problems by now. Amy's not going to share today? Well, who's going to answer the questions? What if I don't do them and Amy doesn't do them and Conrad doesn't do them? We're stuck. You got some numbers? Good. What do we have? 331.2 grams per mole. 331.2. And this one? 223.2 grams per mole. I would hope we've got some people checking. Any checkers? We like them? We like them? Excellent. Triple checkers? Anybody else checking? Did you really check? All right, good. I thought maybe I would get a, yeah, I checked. Yeah, sure I did. Let's check. So let's now go through our calculations. I want to find moles, right? Moles is grams over molar mass. Moles is equal to grams over molar mass. I have 3.31 grams of lead nitrate over 331.2. Gee, do you think that number was picked nicely to get a nice number? What do we get? .001 something, .0009, 9999, so 96. So 0.0, another zero? Is there just one zero? There should be two, I think. 0.00, right? And then 9999. It just goes a whole bunch of nines. That's a real pain. 3 nines. You know what we could do? We could round that up to 1. Why don't we just keep 999? How's that look? That good? Moles. I know it's an ugly number. I think the idea was to get 0.1 if we rounded it, but that's okay. Now we need the mole ratio. There's my 0.0999 right underneath there. We could write it in if we'd like. 0.00999, which means x over 0.00999 is equal to x over this is equal to 2 over 2. That's handy. It didn't matter, right? 2 over 2. 2 over 2. And therefore, x is equal to, what's that? The same thing. So this is going to come up here, right? Remember the opposite operations. 2 divided by 2 is 1, right? So we get 0.00999 moles of this. And that's PbO. Now we're going to go back the other way. We want grams. Grams is equal to molar mass times moles. Grams is equal to molar mass times moles. My new molar mass of lead oxide, 22.3, oops, 223. Ignore that decimal there because I can't erase. My erasing doesn't work here. I'll scribble out the decimal. 223.2 times 0.0099, and I apologize for rolling right off the page there. 0.0999. And how many grams is that? Should be 2.2 something. 2.23? 2.23 grams. Okay, there we have it right there. That is our theoretical yield. So we used our stoichiometry, our 3 calculations, to find the theoretical yield. Now I'm running out of room on this page, but I'll try to squeeze it over here and I'll use a different color. I'm going to squeeze it into this hole and you guys put it down below. Percent yield. And I'm going to avoid the equation, but you should write it down. It's the actual yield divided by the theoretical yield. You can see I've set it up in the question that way. 1.75 divided by 2.23 times 100. And again, you're writing this below where you've got more room. Yep. 78.5% is the yield. So notice how we just add on that last little bit to this type of question. Nothing new here. All right? Oh, goodness gracious. How many marks would that be out of? Probably a couple marks for here, right? I would likely say 1 or 2 marks for there, 1 or 2 marks for, probably 2 marks there. So I'd say 2, 4, 6, 8. I'd say 2 marks for each of those little calculations. 1 for putting the numbers in right and 1 for getting the thing. What's that? Oh, yeah, you might think. It's a little more detailed. Yep. I do have a second example, but I'm beginning to think it's going to be the exact same thing. So I'm going to stop at that point. The second example is there. It's, oops, I'm going the wrong way. Head down. It's one like that. It's got some kilograms in it, but no, we're not gonna do that particular example. So let's go to the question sheet. The question sheet is on. What's wrong? Yeah, you'd put it times 10 to the 3 on it. Let me just address this for a moment. If you get a question that has kilo in it, all right, and you see, this isn't on your periodic table, but it's on the last one, and if I were teaching this again, I would change the periodic table. It's on the one I use in the 3U. Whenever you get kilo, simply for the letter K, put in a times 10 to the 3, and then grams. Because in the metric system, the letter K stands for 1,000. So when you put it into the calculator, you'll put in the first number just normal, 1150, and just like I've taught you in the past, you'll use your EXP button or EE and then put 3 times 10 to the 3. And that will turn it into grams because kilo literally means thousands of grams. Yeah. And I would tell you that that was times 10 to the 3 because it's not on our chart. I should put it on the chart. The same is true for milli. If you had milligrams, so if you had milligrams, let's say you had 270 milligrams, does anybody know what the prefix, why did I turn that to a 3? Does anybody know what the prefix milli is in terms of powers of 10? It's really small. It's actually the opposite. What do you put if you're talking about the opposite in terms of powers of 10? Times 10 to the negative 3 is milli. Times 10 to the negative 3. And again, if you ever needed that, I would give you that information. So that times 10 to the negative 3 is milli. Each of the prefixes in the metric system simply has a times 10 to the power, which you can put in the place of the letter. That's why we use it. It's easier than writing times 10 to them. Anyway, I'm going to stop there. There's a question sheet on Google Classroom, which you can practice on. And yeah, you can work away. Tomorrow we've got a lab, and I believe it's already posted. If not, I'll post it in a moment. I'm going to stop my video.